Hello. So we can start today's session. So it is interactive live session on week 11 videos. So the recap of week 11 is image restoration, image deblurring, image restoration. It is week 11. Okay. Image deblurring, Hadamard conditions or well posed as regularization. So these are the topics covered in week 11. So in image restoration, one question is image restoration is a subjective process, true or false? So what is the answer? So the answer is false. Image restoration is an objective process because subjective means image enhancement is a subjective process. Okay, image restoration is removing noise from the image, so it is an objective process. So we have a clean image F, so that will be converted to G using some degradation function H. So if we have F and if we have a known H, then we can find G. So that is a forward problem. But in the case of inverse problem, that is what we are interested in, because we have a degraded image G. From that we have to find out the clean image F. That is our aim, right? So it is an inverse problem. So inverse problems are image deblurring. Image deblurring means we have a blurred image, we should convert that to sharp image. Then image super resolution is we have a low resolution image, a small sized image like 100 by 100. We have to convert that to 500 by 500 or something. Okay, that is meant by image super resolution. So small image should be converted to large sized image. Then comes image dehazing. Image dehazing is if we have hazy image will be looking like background hazy, so that should be converted to a normal image. And roll shutter geometry correction is, rolling shutter I think it was explained in the first lecture. So due to the rolling shutter camera, it's a rolling shutter, so the exposure of every sensor element, every sensor row will not be the same because of the rolling shutter effect. So in the captured image, scene content may be a straight line, but the captured image may contain that straight line will be converted to that a curve. So this type of distortion is known as geometric distortion. So a straight line will look like a curved line when there is any motion. So that is known as geometric rolling shutter correction. Then so next we have one question, write the image formation model of a hazy image. So that is given in the lecture. So we have a hazy image G of x, so that will be some transmission map f of x. So haziness will be increased as we go through depth, right? So if you are captured a hazy scene, then in our image the nearby points will be clear, but far away points will be hazy. So it depends on the depth of the scene points. So that depth comes here in t of x. So e raised to minus beta t of x is beta depth is t of x. So t of x will scale this f of x. F of x is the original image. So original image is the clear image. So clear image will be multiplied by some factor of some depth. So as depth increases, t of x will be reduced. So that scaling will be given to the original image. So the original image will be decayed at higher depths. Then we have some more term, 1 minus t of x is equal to into a. So a is the global background light. So this is the image formation model for a hazy image. Then we have image deblurring. Image deblurring is like we have a clean image f. So while capturing a photo, we'll get a blurred image, right? So that formation of the blurred image can be represented as the convolution with the PS of h. So in frequency domain, or we already wrote g equal to hf plus n, right, the previous classes. So n is some noise. So this is our blurred image, g is our blurred image. Then in order to do the image deblurring, we have to use some restoration filter here. Okay, so that restoration filter should have the knowledge of h. So what function will give this blurred image? So this restoration function should have the knowledge of h, otherwise it is ill-posed problem. Okay, ill-posed problem. Then so inverse filter can be used, and along with that we should have some prior knowledge of this f. So if we have some prior knowledge of f, that also can be added. So we don't know the exact f, but some characteristics of f we know, some characteristics of clear image we know. So that prior information can also be included in the restoration filter to get the restored image f cap. So this is the case of image deblurring. So we have two types of deblurring, non-blind deblurring and blind deblurring. In non-blind deblurring, h is known. So the function that causes blurring is known. But in the case of blind deblurring, h is unknown. The function that causes blur is unknown. So in that case, h also need to be found out. Okay, so h along with f is the problem here in blind deblurring, h and f. So it is an ill-posed problem. So in all the cases we have some equation like y equal to some function of x, right? So in all the cases for inverse transform, inverse filtering, not inverse filtering, for every inverse problem we have to find out x from y, right? Y to x mapping should be done. We have to find out f. So say we have this domain of this transformation x is here, then we have codomain of this transformation y is here, and every f will be mapped to this small region G. Okay, then there are actually three conditions for a solution for a well-posedness. Okay, so three conditions are: for every G, for each datum G in Y, so every G should have a F, every G should have an F. So that is one condition. Then so solution should exist. So the first condition is existence. Then the next condition is for every G we should get only one F, not two F. So that is meant by uniqueness. So F should be unique. Then comes numerical stability. Numerical stability means if if x1 is one point and x2 is another point, they are very close. So y corresponding to x1 is y1, y corresponding to y2 x2 is y2, then y1 and y2 should also be close. So this type of condition is known as solution is numerically stable. Otherwise, if we have x1 and x2 very far away, y1 and y2 should also be far away. Okay, so the difference between these two, relative change between x1 and x2 should reflect in y1 and y2 also. So the first case we can take existence. So there should exist one solution. So we have the normal equation Ax equal to y, where A is a matrix of size m by n and n is a vector, a column vector of size n by 1, and y is a solution, y is a blurred image, okay, m by 1. So we have to calculate the function. So we have to find out, we have to find out this x input image, right? So x is the solution of this equation. So if the solution is not exist, because if you have x and y, so this is the codomain, but y lies here, so it is not in this region, but every x should be mapped to this region only. So no y can be mapped, no such a y can be mapped to x, right? So we have to find out the closest y inside this RL such that that can be mapped to x. So that closest thing is we have to find out. So such an x we have to find out, that is x cap. So what we are doing is ax minus y, it should be ideally 0, but it is not 0 because ax is not equal to y. Correct, that mapping is not available. So we have to, one thing we can do is that we can minimize this function. What x minimizes this function, that x we can take as the solution. So that solution is known as linear least square solution. So by deriving this thing, so we can write it as like this. So it is given in the lectures, and we will take the derivative and equate to 0 to get x cap as A transpose A whole inverse A transpose y. So this is the linear least square solutions. Okay. So prove that projection matrix from y to y cap is idempotent. So what is y? Y equal to ax. But x cap using linear least square solution, we got A transpose A the whole inverse A transpose y. So what is y cap? Y cap is the point inside this R of L. So this thing is y cap. Okay. This point is y cap. So y cap will be A into x cap. So original x is not available. So we are finding another x cap that is mapped to y cap only. So that is equal to A transpose A the whole inverse A transpose y. So this is x cap. Okay. So projection matrix is the matrix which project y to y cap. So outside to inside R of L is known as projection matrix. So P is equal to P into y. So P, what is P? A into A transpose A the whole inverse A transpose. So this is P. We have to find out it is idempotent. So P equal to P ratio, and that is we have to find out. So P we know, then P square, first find P square. P square is A transpose A the whole inverse A transpose A transpose A, the whole inverse A transpose. A transpose A into A transpose A inverse is I, right? So we will get A into A transpose A, the whole inverse A transpose, which is equal to P itself. Then P cube is P into P square. P into P square is P itself. So which is equal to P. So P raised to 4 also P cube into P. P cube is P. P raised to 4 is P is P. So P square, which is again P. So if you are taking any n, will get P raised to n equal to P. So we have proved that projection matrix is idempotent. Then we have to find that whether y minus y cap. So y is equal to ax. So we have this x, we have this y set. So here it is R of L. R of L. We have L transformation. So here we have y. That y we are given. Okay. But we have projected that y to y cap. So using a projection matrix P. So our aim is y minus y cap is orthogonal to y cap. That is we have to prove. So its transpose y cap should be 0. So we can find y cap is a x cap. So y minus y cap is ax or px. Okay. So y minus px cap wait. Okay. And we know y is equal to p into y cap. That projection. So no, y cap is equal to p into y. So y minus py transpose py, y transpose minus y transpose p transpose into py, which is equal to y transpose py minus y transpose p equal to y. And we can prove that P, what is P? What is the equation for P? A into A transpose A whole inverse A transpose. So which is equal to P transpose, that we can prove. Okay. So P equal to P transpose, then this equation becomes y transpose Py minus y transpose P square y. But P square is P itself. So y transpose Py minus y transpose Py equal to 0. So we can say that this error, the change between y and y cap, is orthogonal to y cap. Okay. Then which of the following is true for projection matrix P? That we have already proved. P transpose equal to P. Because P equal to A transpose A, the whole inverse A transpose. Then P transpose equal to this transpose. So A into A transpose A whole inverse A transpose whole transpose. A into A transpose A, the whole inverse transpose, then A transpose. A B C transpose is C transpose B transpose A transpose. So A, this thing also first we can apply transpose, then so A transpose A, the whole inverse A transpose, so which is equal to P itself. then P is called orthogonal projection matrix. That is also correct. Okay, so both B and C are correct. Then next question, check whether the metric A is orthogonal projection matrix. So the condition of orthogonal projection matrix is what? Orthogonal projection matrix P should be idempotent. Idempotent means P raised to n should be P and P transpose equal to P. So here we can verify that A square equal to what is 0, 0, 2, 1, 0, 0, 2, 1. So we will get 0, 0, 2, 1. So we will get A. So for A cube also A square into A into A. Similarly, okay, A cube, A raised to 4, etc. So you are you will get A raised to n as A. So first condition is satisfied, but A transpose is what? 0, 0, 2, 1. So that is not equal to A. So this matrix is not an orthogonal projection matrix. Then comes the case of uniqueness. So F should be unique. So we have X, Y. Here we have Y should be inside this. Otherwise we can use linear least square. So if Y is inside and X is here, so we can have x1, x2 like this. Okay, but we can choose mod x such that its magnitude is norm is very less. So the condition is we have to minimize this mod x square such that Ax equal to y. Okay, then after solving this we will get this solution as A transpose inverse y. So this is the minimum solution for x. So what will you do when A transpose is not invertible? We have to find out, anyway we have to find out what inverse, right? Because the solution is having this inverse. But if it is not invertible, what will you do? So you can find out pseudo inverse using SVD. How? So in SVD, a matrix A, so here a matrix B should be represented as U, D, B transpose, where D will contain some sigma 1, sigma 2 like that. Then D inverse will be, so you have to, this thing in last lectures it was covered like 0, 0, 1 by sigma 2. So here we have U inverse and B inverse transpose. So that thing, so this is pseudo inverse. Then comes numerical stability, that I have already explained. The relative change in x should reflect in relative change in y. So if x and x1 and x2 are very close, y1 and y2 should also be close. Okay, so the condition is what? So we have the relation between y and x as Ax. Then the condition can be derived like this. So mod x, so delta change in x by x should be less than or equal to A inverse delta y by y. So here, in order to make this change in x and change in y closer, this mod A inverse should be minimum. So that value is known as condition number. So condition number of A. So that condition number can be derived as singular value, maximum singular value of A divided by minimum singular value of A. that is condition number kappa of A. So so we have to check whether this condition number is less or more. If it is more, we can say that the solution is not stable. Okay. So one question is, let y equal to a of x, then y1 equal to b x1. So you have two equations, y equal to ax, y1 equal to b x1. You have to find out which equation is stable. Okay. For that, it is given that eigenvalues of A transpose is this one, and eigenvalues of B transpose. So eigenvalue means lambda of this one are A transpose is 10,009 9801, and lambda of B transpose is 10,009 and 1. So the question is, which solution x or x1 is stable? How will we calculate? You have to find out the condition number of the matrix A or B. Condition number can be written as singular value of A divided by minimum singular value of A. Here maximum singular value of B divided by minimum singular value of B. So you are given eigenvalues of A transpose. So from that, how will you find out singular value? Singular value of A in SPD we did like that, right? First we will find A transpose. So its eigenvalues we will find out. Then we will find the square root of those eigenvalues to find singular value of A. So singular values A are what? 10,000 square root is 100, then 9 square root 3, then this square root is 91. 91 or 99? 99. Then singular values B is square root of this one, 100, 3 and 1. Then just find here kappa of A, maximum singular value is 100, minimum singular value is 99. Kappa of B is 100 by 1. So this is approximately equal to 1. So its kappa is less. So the condition number of the first matrix A is less, but condition number of second matrix is 100. So we can say that the first equation is more stable than the second. Okay. So the here we should remember that the singular values are square root of the eigenvalues of A transpose. Okay. Then comes inverse filtering. So for image deblurring, if you have an observation like this, G is equal to HF plus N, so G is observation. In frequency domain, we can write it as G of KL is equal to H into F plus, so G is equal to HF plus N. And if we know the blurring function in Fourier domain, we can just divide that to G by F to get F. G by H. So if we know the blurring function H, then just divide that by H, we will get F plus N by H. So our aim is to get F only, right? But there is a noise also during blur image formation, so that N is also divided by H. So H is a deblurring function, so blurring function, right? So H will be looking like a low pass filter. So in high frequencies it is very less. So in high frequencies it is very less, so this term will be very high at high frequencies. So we have to choose such a low pass filter that should not be very less at high frequency. So we have to fix an epsilon like this, and if it is more than some omega, more than some frequency, it should not decrease, it should be constant as epsilon. So that is a case of inverse filtering. So one question is, what could be the value of epsilon you choose for images A and B for inverse filter? So if you are increasing, if so that looks like this, right? This is your H. So if you are increasing, if you are making sigma to here, like if it is close to 1, it is not looking like a low pass filter, right? So it should be looking like a all pass filter. So what will happen? So if it is close to 1, then the filter image will have less noise but will look very smoothened out. It will not be like a sharp image. So our main aim is to sharpen the image. That aim is actually lost, but noise will be less. But if we are decreasing epsilon to 0, what will happen? The low pass filter will be looking like this. So low pass filter will be there. So by using H of F as inverse filter, the image will be more de-blurred, but along with that noise will be increased. So what should be epsilon for A and B? So in the case of A, what we are doing, epsilon is increased to 1. Here epsilon is decreased to 1. So in the second case, the image becomes more sharp but noise is more. But in the case of A image noise is less but image will be blurred. So the answer is A, 0.94 A and 0.14 B. Then regularizing a solution. So in least square model, we are only taking y minus ax to be minimum. Instead of that, we can use a knowledge of x also as the regularization term. So it can be proved that, so our solution becomes like this: x cap equal to A transpose A, the whole inverse, A transpose y is the general equation, plus some lambda q transpose q. So this term will give that kappa term, that condition number to be small. So regularizers are used in this linear least squares models. There we are introducing some knowledge of input image. Then lab assignment 11. So the question is to perform non-local mean filter. So in non-local mean filter, this is a filtered image f cap. So we have input pixel p, and we will take a patch np like this, and we will take another patch here nq, and we will compare those two patches. If the patches are similar, that will add more weightage here, and that will be multiplied with this g of q. G of q is the intensity at the pixel q. Then that weightage will be given to this p. So if the patches are very different, this Gaussian filter will not give any weightage to g of q. So that is the aim. So in the question, some filters are given. Search window size and similarity window size are given. So search window, I think Okay, search window size is 5. Similarity window size is 3. So the thing is that take a pixel P. Okay, take a pixel P here. You can see here, right? So take a pixel P, then take the similarity window size 3. So 2 into 3 plus 1 is 7 by 7. So the size is 7 by 7. So you can see this green patch, right? So that 7 by 7 patch you have to take. Then you have to take another Q. So where should be Q? Inside the search window. Search window is 11 by 11 size. So around pixel P you have to select a search window of 11 by 11. 11 by 11 is the black square. So inside that you have to take every pixel as Q and its similarity window you have to take. So if you are taking this blue Q, this blue color Q, Q1, then you have to take patch around it. The patch size should be 7 by 7. Then you have to find out the difference between this patch and that patch using this this equation, e raised to minus Vp minus Vq the whole square. Okay, so like that. So you will find the weightage, normalize it, and then find the f of p. Okay, so that is the question. You are given different patch sizes also. So that's all about today's session. So if you have any doubts, you can ask. Okay, then okay, thank you.